My talk today will be about developing search engines, especially about developing intelligent search engines. Part of this work has been done at the Humboldt University as part of my PhD thesis in cooperation with Tobias Schäffer. Okay, we will talk about searching the World Wide Web. What do we find in our World Wide Web? Well, of course, we find several web pages over there which have textual content which we want to analyze and search. And of course, we can use the links in between those pages for getting additional information. Throughout this talk, I will be talking about inlinks of pages. These are those links pointing to your web page. And I will talk about so-called outlinks of web pages. These are links that come from your web page. Well, that's basically the World Wide Web as search engines see it. Okay, so these are the three main topics I will be talking about. First block will be about the basic architecture of search engines, but this will be a rather high-level description. The second talk, or the second block, will be about how can machine learning help us build more intelligent search engines? We will focus on two subtopics, namely fighting link spam, that is, pages trying to get a higher ranking by using some kind of suspicious techniques, but we will see later on which these techniques are and which techniques we can use to identify these pages. And the second topic we will concentrate on is how to improve the user interface of search engines. That is, at the moment what you see is only flat result listings, and maybe you want to group web pages of common topic in one block so that you can cluster, for instance, results for ambiguous queries. And last but not least, I will present you some projects that you can take part in yourself if you want to get into the field of search engines. But let's start with building a search engine from scratch. What you see here is what you basically will have to cope with. On the left side, you see everything that deals with getting pages, storing them on disk, and kind of validating them. And on the right-hand side, you see everything that is rather dynamic and deals with retrieving queries and finding pages that match those search queries and presenting them. If we want to build a search engine, what we first need to do is get the whole content of the World Wide Web. How can this be done? Of course, we do not know all the URLs that are out there, so what we do is we choose some starting pages. So it could be, for instance, the who directory, it could be demos, whatever you like. So what you do is add all those URLs to your kind of list of pages you want to crawl, and then you start a little program, and this might get, for instance, these three first web pages. What you do next, you have to analyze those pages and kind of find out all those links on these pages, and you can, of course, follow those links, and sooner or later, you will end up with all your web pages that you wanted to crawl in your repository. So to sum up what you do, you choose your starting page, you get the page content, save it on disk, and extract links from those pages and follow them recursively. Sounds rather trivial. What makes it less trivial simply is the size of the World Wide Web. So first thing you want to do is parallelize crawling. There are web servers that react rather slowly. There are others which react rather quickly to your queries. So in the meantime, while others are still processing your request for a web page, you could easily start querying another web page in the meantime. Next thing you want to do, of course, is prioritize the links, so that after crawling, what you end up with is the most important pages are already in your repository, and the less important ones maybe are postponed to a later point in time. And last but not least, webmasters, of course, are not very happy if you scroll all those pages in about, I don't know, 2 minutes. So what you have to kind of keep in mind is that you do not gather too much content all at once, because this would kind of look like attacking the web server, and you do not want to do this. Okay, so now what you have is a large repository with a whole bunch of web pages and all their content in it, and what you basically could do is run grep over all those pages and retrieve everything that matches. Of course, for the whole World Wide Web, that would not be very efficient. So what you really want to do is build an index. How do you do this? Well, you parse web pages and extract every word on those web pages. You might leave out unimportant ones, like for instance, it doesn't give you very much information. What you also want to do is, for those pages where you do not have the content, you still have information, because you know about these pages because there are links linking to these web pages, and attached to these links there are anchor texts. So what you can do is simply attach these anchor texts to your web page and add them to your index. After you have this bag of keywords for one URL, what you do is you create an index. It contains all keywords you have ever seen, and on the right-hand side you just attach all URLs that match the keywords in this list. So let's have a look. What we have here is a very, very small index. It contains only 2 terms, basically the abbreviation of today's Congress and the term chaos, together with 2 URLs. Suppose you encounter this web page there on top. What you do, you extract the first line of content, and you parse it word by word, add the URLs to your index, like private, investigations, 22nd, and so on, until you've parsed the whole sentence, and then you go further. So what you end up with basically is a list of keywords and URLs on the other side. Okay, what do we need all this work for? Basically, what you want to do is answer queries. So for answering queries, what you do is you get your query from the user, maybe in a parallelized way, because there will be many, many users which want to query your cool search engine. Then you go to your index, find matching pages, and because there will be many, many pages matching, say, the Chaos Communication Congress, you will have to rank the results and return them in some kind of easy-to-read way. Okay, that's it. Suppose you search for the Congress today. In our index we've just created, there are 2 URLs that match these ones. Then you basically pass them to the ranking algorithm, and this algorithm somehow finds out that the Congress web page is a little bit more important than the web blog of Fukami. What you do is generate a ranked search result listing. Okay, seems very easy. But in the next block we will see why this cool ranking stuff is not so easy. Basically there's at least one major problem, and that is you do not know what your user actually is searching for. Suppose you have the query for Panther. Who tells you whether the user actually is searching for a car or whether he's searching for an animal? So what you will do in the easiest way is use a kind of mixture of text-based relevancy for your query. So basically you will retrieve pages containing the term Panther, as well as pages that are pointed to by links which have the anchor text Panther, and you will compute some overall importance of your web page. Okay, the first question that arises is, what is an overall importance of your web page? Well, since the end of the 90s, there's this measure called PageRank, and we will have a look at it on this slide. The equation might look a little bit difficult, but indeed it is not. It's really trivial. So PageRank expresses some kind of link popularity. It is based on a random server model, So suppose you do not have any purpose when surfing, you only can do two actions. You either can choose from the whole repository one web page at random, or on the other hand, you already are on a web page and you can follow links randomly. So what you see here, alpha just is the probability for the server not to follow a link, but to choose one link at random. And this term below alpha simply gives you the size of the whole corpus you have crawled. And so basically, this term gives you the probability of your server to jump to your web page at random. It should be rather small. On the other side of the formula, with 1 minus alpha, of course, your server will decide to follow one link at random from the page he already is on. Suppose your server is on this Congress web page and you want to compute the page rank for the Mozilla page. Assume you only have this one link to your Mozilla page. I know that this is not correct, but for this little example, it should be okay. So what you do, you sum over all inlinks of your Mozilla page, and then this Mozilla page gets the page rank of the source of your link divided by the number of links the source page has. Let's have a look at our animation. We assume we already have the page rank values for the two pages on the left-hand side. In the first iteration, we just distribute both values to our page in the middle. And because this Congress web page in our example has only two outlinks, page rank is split up between this KDE page and Mozilla page. That's all. So, okay, what do you have to do to spam search engine rankings? We have seen that we rely on textual measures. So suppose you want to rank high for search engines and Chaos Communication Congress. What you will do is put those terms into your web page. You might even put them into headers and in boldface so that search engines think they are really important parts of your web page. Next thing you will have to optimize is your page rank. How can you do this? You just convince all your little friends to link to your page. And we have also seen that search engines rely on anchor tags. So what you do, you just convince them to put specific anchor tags to their links. Okay, what do people actually do to boost their page rank? One nasty way of boosting your page rank is automatically searching for pages you can edit, such as wikis, guest books, whatever, and add your target URL to these wikis. Another nasty thing you could do is simply buy links to your target page. Just go to pages with high page rank and you purchase links from them. Next nasty thing you could do is write a script which generates you a whole bunch of pages. They might be rather similar, and you just interlink them. What you basically do with this setup is collect up this random jump page rank in this network. And last but not least, you have to distribute, of course, page rank to your target web page. Rather simple. And then, of course, there's this little funny example about Google bombs. So if you are searching for miserable failure, what you will find, of course, is the CV of George W. Bush. Of course, he does not have these terms on his web page. So what has happened to him is, again, our little example, we have the Congress page in the middle. We have a whole lot of people. We have convinced them to link to our target page, and we have convinced them to put an anchor text to these links. In the case of George W. Bush's CV, what has happened in the middle, we have his CV. We have a whole bunch of web pages linking to him, and each and every link that points to him has this miserable failure in its anchor text. So basically, without those term on his page, he will nevertheless rank very high for this query. Okay, this summer we have done experiments on classifying web pages into spam and ham. So this was one first experiment for the machine learning community. So what we first have to define is what we consider to be link spam. Suppose you're searching for medical trials for some kind of medicine. You get, well-known ranking, and you think, okay, there's the first result, and I think it's quite important, and it's quite relevant. Okay, what does this page do? It doesn't tell you anything about medical trials. It just tries to sell you Viagra. It's not really what you were searching for. Okay, what you might want to do is issue this links query. You can do it with Google, you can do it with MSN. I don't know whether you can do it with Yahoo, but I suppose you can. So what you find are all those links, linking to pillwatch.com. So you have a link from the town of Florence, you have transportation links, so you have a whole lot of unrelated links. Okay, what we think is link spam is simply a page that ranks high, in our case, for medical queries. The page does not match the query, such as we have expected, and it receives a lot of unrelated links, so it's a spam page. Why would you want to classify pages into spam and ham? So what you see is that PageRank simply represents the probability of your random server coming to your web page, just by randomly following links or starting newly. So PageRank assigns weight to your web page according to this model, and of course spam disturbs this coupling between importance and links. So what we did in summer was identify two types of link spam, just to keep experiments in a rather well-defined setup. So we concentrated on link exchange and link farm pages, as well as on guestbook spam. Okay, first thing you have to think about is how do you actually build a web page classifier. What you want, you have the web page up there, you have kind of a black box in the middle, you stuff the web page in, and the black box tells you whether it's spam or ham. As black box, I don't know whether you know it, we use the support vector machine. If you're not familiar with support vector machines, just stay right here. After my talks, there will be a presentation about support vector machines, so I just left out all those little details about the classifier. Okay, basically what you do is kind of build a feature vector of your web page. I will tell you what those numbers actually were in my experiments. To simplify, I here have only a feature vector which describes two attributes of our web page. Clearly that is not enough to find out about spam or non-spam, but in this example it's a little bit easier. With this vector, what you can do is you can draw a coordinate system, and you will find your web page over there. That's basically why I used only 2 dimensions, because drawing a 1000-dimensional coordinate system on a slide is a little bit tedious. So suppose you will also have a lot of other positive examples over there, and of course you also have some spam examples over there. What your support vector machine should do is find a hyperplane that distinguishes ham from spam, so that all ham is on one side of the hyperplane, all spam is on the other side. So what you can do after that, when applying your classifier, is you have an unlabeled example and you just find out whether it's lying on the right-hand or left-hand side of your hyperplane, and this then can tell you whether it's ham or spam. That's the basic principle. Okay, what you need labeled training examples, because based on them you can compute your hyperplane. You somehow need to represent them in feature space, and you need to train your classifier. And after these 3 steps, basically, you can apply your classifier and you can then compute whether you have a ham page or spam page. Okay, we are dealing with link spam. So what we will need is not only the page itself, but also the link neighborhood to find out whether there are suspicious links pointing to it. So what we did, we want to classify our little page in the middle. I hope it will be ham. So what we do, we choose a search engine of which search engine ever you like. I choose MSN because Google somehow filtered out the backlinks of spam pages. What I did then, I used an open source search engine, it's Nudge, and crawled basically the linked neighborhood of our page. All those gray pages were those retrieved by Nudge. Then I extended Nudge such that I could compute several link-based features. What are those? I thought maybe the length of the URL could be interesting, the number of inlinks. It could be interesting how long the description actually is. And for this example itself, I also extracted the text, and I computed so-called TF-IDF vectors. TF-IDF simply computes one dimension per word in your dictionary. So you already see that this will be a very high-dimensional feature vector. And for each word that appears on your web page, you kind of have a weighted entry in your feature vector. Okay, those link-based and those interlinked features were computed once for our web page itself. And then there was one subsection for averaged values of all inlinking pages and one subsection for averaged values of all outlinking pages. So what we have here are some basic statistics about our page as well as its neighborhood. Nothing really spectacular so far. What we also thought, there's research in theoretical physics about measures which are characteristic for naturally grown networks as well as for synthetic networks. So there's one measure especially interesting for us. That's the so-called clustering coefficient. I will explain it on people because that's easier. Suppose you have Fukami in the middle, and in our model, Fukami knows 3 people. And among these 3 people, 2 people know each other, but basically not only these 2 people could know each other, but there could be 3 links in our model. So we get a clustering coefficient of 1/3, which means there's 1 link where theoretically there could be 3 links. Of course, you can do the same for web pages. You have your example in the middle. You find out about all those pages that are connected to it. And basically, again, you compute the ratio between how many links do exist versus how many could theoretically exist. Okay, next thing we thought about was link farms tend to be automatically created. So those linking pages pointing to your target should be rather similar. For instance, they could have the same length, they could be on the same server, having the same IP address, they could have the same link targets, whatever you can imagine could be similar. Again, let's have a look at our example. We have this page to classify in the middle. We look at those pages connected to it, and in our case, 3 of 5 pages are actually equal. To make it more easy to see, I've made them equal in content, but you can, of course, imagine that you can make this measure based on IP address or whatever you like. Okay, trivial link farms even could reside on the same server as their target web page. Rather stupid thing to do, but well. So what you do is compute the same thing. You just have a look at this link neighborhood, and among those, how many of them are similar to your page to classify. There are 3 pages similar, or 2 pages similar to your example page. So what you end up is with 2/5 of the whole link neighborhood are equal to your example page. You can stuff all this in your feature vector of link features and use it for training your classifier. Okay, now you have a nice classifier, but how do you actually evaluate how good it is? If you're a search engine provider, what you can do is have a look at the ranking of your search engine and have a look at which result does the user click on. If the user always clicks on the second, third, fifth result, but never on the first one, then maybe your ranking is not that good as you expected, because, well, the first result seems to be not interesting. If you are an internet provider, what you basically could do, if you have enough users, you could compare the ranking versus the actual traffic on the web page. Of course, Humboldt University is neither representative for providing search engines, nor is it representative as an internet provider. So what we basically did, take a student, put him in front of a computer and tell him, okay, please label, well, this portion of the World Wide Web. Okay, he did not have to label all the World Wide Web. So you can use demos as some source of ham pages which should not be spammed. And there is, I don't know whether you know it, it's this weblog software, movable type, and you have a plugin with a list of regex expressions for weblog spammers. So this you can basically use as a source for guestbook spam, but well, for the link exchange pages, we still need our student. Okay, that's what we have. These are only two curves of the whole publication, but I suppose if you have a look at it, there are some more. What you can see here, the red curve basically gives you the performance of a classifier that's only based on the text of the web page. No link features, no context similarity, nothing, only the text. And the little purple curve as well as, yes, the purple curve is only based on the link-based features, so only context similarity and also average statistics stuff. And I don't know whether in the last row we still see the light blue curve. It gives you the performance of a feature vector which is concatenated link features as well as text. So what we see in these graphs is that link features basically for both classifying guestbook as well as link farm spam performs better than text-based classifiers. So graphs on the x-axis, what you see is that we grew the training set. For guestbook spam, we basically started with 11 examples, which we gave to the classifier to train on. Next step was to train on about 300 examples, next step 500, and then 1,500. So, and on the y-axis, what you see is the so-called AUC value. It's, at the moment, it's rather popular in machine learning. It simply gives you an evaluation of how good your web page, how good your classifier is. It gives you the probability, so it should be scaled between 0 and 1 of, suppose you have a positive and a negative example at hand, how large is the probability of giving the positive example consistently a higher value than your negative example. So suppose you have a row of positive examples and negative ones. If you first get all those high-valued positive examples and then low-valued negative ones, you just can put a threshold on this classification value and then cleanly separate ham from spam. If you just have positive, negative, what you basically could do is toss a coin and get the same performance. So that's not what we want. We also ranked our feature vectors, and what we found out basically was, lucky enough, in-link and out-link counters like average number of in-links, average number of outlinks based on in-linking pages, out-linking pages were very important. But what was also important was this clustering coefficient. You remember the picture with Fukami in the middle. Okay, so far we have evaluated our classifier only in a static context. We did not take into account that there are actually people probing our classifier and trying to break it. So what we have to do is view our classifier in some game theoretic context. On the one hand, we have our spammer trying to probe and break our classifier. On the other hand, we have the search engine trying to deliver us with important and interesting information. What we could gain from viewing search as such a game theoretic problem would be whether there are any kind of equilibria in this game, Or what we could ask the question whether there are actually unspammable ranking criteria. But this is still an open question for research. I have done some experiments, but you can easily look them up in the paper. Okay, so far we have seen how we can build a search engine, how we can use machine learning to fight link spam, but of course we can use it also for improving on flat result listings. As I said before, there are many queries which are actually ambiguous. Suppose you're searching for Panther, for clustering, you could cluster search results as well as building a Linux cluster. How can you handle ambiguity? You can simply cluster search results. So what you end up with groups of topically related web pages. And this information also can add some additional context to your query. There actually is a search engine already working. That's Vivissimo, and you see on the left side that there I've been searching for CCC basically. So there's of course the Chaos Communication Club, there's a chess club, a cycle club, whatever. And what I think is especially interesting about this presentation is that you get an overview of topics related to your query without leaving through hundreds of result pages. Okay, what is also done in research with machine learning? You can imagine most queries commonly consist of 1, 2 query terms, not much more, if you're not searching for anything very specific. So what you might want to do is extend your query with an additional category information, especially if there are terms that are synonyms to your query. You might want to extend it to find other related pages. So what has been done this summer for the KDD Cup, Knowledge Discovery and Data Mining, is people were given about 1 million queries and I think 2 or 3 months of time. And what they had to do is categorize those 1 million queries into 8 categories. There were only about 70 to 100 examples. So what you had to do basically was query some search engine to get additional information for each query. So there were 20 international research groups taking part in this competition. And actually what was really fun about it was that Humboldt University has actually won the runner-up award. So that was really nice. Okay, if you look at today's search engines, what you see is you have to enter already the terms which you expect to find on your target page. How about issuing queries to your search engine? Wouldn't this be some kind of even more, well, fun if you have kind of questions? So there are some kind of prototypic implementations already online, but it's still a difficult research question. So here we have such a prototypic implementation. We have asked it about when was the CCC founded. If you ask this question to Google, you will have to leaf through all those search results, and you will have to actually search for the answer in all the results. What you see here is already in the first result that CCC seems to be founded in 1981. So as the information has been found on the CCC page itself, I suppose it's correct. Okay, let's come to the last point of our agenda. We have seen so many interesting questions and so many interesting research problems. How can you contribute to them? First of all, search engine and building search engines is a really big topic. So I would not suggest that you really start from scratch as we have done in the presentation. There are so many obstacles to take and so many projects which are already established and still alive, so that you could easily start out also working on those projects. I will present you 3 interesting opportunities. The first one, Google actually gives you the possibility to automatically query their index with the Google API for building small, fast, standalone applications and for playing around with search engines. That's probably the right thing to begin with. Second opportunity you have, you can just use a standalone search engine such as Nudge or ASP-Seek, and you can take part in developing, I suppose it's spelled JC, which is a peer-to-peer search engine. So what is the Google API? You just can download it for free. It's very clean and easy to read source code, so it would take you about 15 minutes to set up your first little example. What you need is this example source code, and you will get a personal API code key. What is the reason for this key? Well, basically, Google tries to keep the traffic under control, so you will be allowed to issue only, I don't know, about 2,000 queries per day. But it should be enough already for starting little examples. And with that API, you can write your own applications that automatically query Google Web Search. What have people done with it? Someone has built a family tree. You can put some name into this application and it will try to find out about father, mother, sister, whatever. What else have people done? Someone has created some kind of fortune cookies based on Google. It just generates you random theories. Then there has also, of course, is a Google image search API. So what this guy has done, he just has set up a little riddle. He issues a query to Google image search, presents you the images, and asks you, well, what have I been searching for? So, well, there's a lot of beverage on this slide. Actually, a lot of Fanta. So what the guy has been searching for is Fanta. But there are a little bit more difficult riddles also. What have other people done? There have been people analyzing web logs for the age of the person who has generated the weblog. I have been in Switzerland for the last 2 months, so I have just issued the query Käsefondue, which is cheese fondue in English. So what you see is that there are few young people writing about it, few older people, but in the age of, I think, 25 to 40, there are a lot of people interested in this food. Okay. If you now have played with Google API, you might want to create your own search engine. I would suggest you go to Nudge. Unfortunately or fortunately, Nudge is built Java, so there might be some performance problems, but it works really good. I've used it for my publication. So it's an open source search engine implementation. You have online documentation. You can get the source code like in a minute. It's hosted as an Apache project. So what you can do with it, you can extend it to your own needs, as I have done for my publication. Or if you do not have that much fantasy, of course, you can also go to the issue tracker and solve issues posted there. I suppose there are many interesting problems that you could still solve there. For ASP-Seek, it's also a search engine open source project, but as far as I can tell, it's been rather quiet during the last time. So I don't know whether I can recommend that one. So what you see here, Creative Commons has actually this search engine running, and you can search for Creative Commons content. So with Nudge, you also have one very good advantage. If you have any questions, just read the mailing list, and if you do not find an answer, just ask your questions. Within 1 or 2 days, you should get an answer. So what is interesting about this application of Nudge is that you have this little debug button over there. What happens if you check the button simply is that you can find out about the whole computation of the weight of your search result. So you actually can see why it is ranked first and not last. Okay, last project I want to present is JC. It's a peer-to-peer search engine. So what is done here, you have a crawler and indexer distributed amongst many PCs. Everyone basically running JC is meant to open his computer for publicly sharing this created index. So each query basically is shared amongst all PCs. So from the project homepage, what you can get is the source code of this engine so that you can take part in the development process, but you also get a package which you can install like out of the box. So it took me about, I don't know, 15, 30 minutes to set it up, so it's really simple. Okay, here's JC now running, this time searching for chaos, but I think the index is not yet that large. Okay, to conclude, we have seen several interesting tasks in search engine development. There are tasks on the research side, where you can still write interesting publications about, but there are also many tasks that are related to implementing search engines. So search seems to be kind of an unsolved problem. If you hear the term search engine, you just think, okay, there's Google or there's Amazon, and I just get the right results. But there are still many interesting and open tasks which you can solve. And many of those also have to do with automating things with machine learning. You don't want to put a lot of people in front of computers to classify web pages into spam and ham. You want this to be done kind of magically. What I would like to advise you to do is not to start from scratch, as basically the topic is really broad. So go to one of those many existing projects and help those people, and I think they will easily help you to take these many obstacles that are waiting for you. Okay, thank you. Are there any questions?
I have a question. Hello, I have a question. And in early December, Alexa started to offer a new service. I didn't actually read the announcement in detail, but it was both. You have access to their index, and they can host web services for you, if I understand it correctly. But there's a fee involved. Is that something that's interesting to you as a researcher?
I don't know how good the budget of the Humboldt University actually is.
Okay, but
sorry about that.
Did you look at it at all?
Yes, of course I know about it. So you kind of have to pay for the service of it.
Okay.
And I think it would not be that interesting.
Thank you.
Okay.
Yeah, I've got a question too. Maybe it's not fitting directly in, but it's the only question I have in mind now. When will Google be kicked out? when will the age come that there is a kind of popular open source search machine?
Well, that's actually...
will it come? What do you think?
I cannot tell you actually. So what the basic problem with open source engines you have, suppose you have already this development of Nudge. You still have with Nudge only the source code. You can have it running, but if you want to have it running privately, what you need is a lot of bandwidth for getting your pages. What you also need is a lot of hard disk space for actually saving those pages, or only for saving the index. So if you have this money, it shouldn't be that much of a problem.
I will take a look, but I don't think so.
Any further questions? Or do you all want to go out for a break and eat something and drink something? Okay.